Lesson 69, a little bit rude, but that's fine. Lesson 69, impulse. We will learn how a change in momentum is caused by an impulse. There's a joke here about like keeping your natural impulses and lesson 69, but we're going to ignore that. What did we talk about last time I had you guys? Last time we were talking about momentum. Now we talked about, I mentioned we're going to go all the way back to the 3 types of momentum. We said firstly, momentum is to a discussion of how a motion of an object is moving. It is mass times velocity. It's a vector quantity, so keep that in mind. It has a direction. We did some basic calculations. We wrapped them up really quickly. Then we said the main thing about momentum. Momentum is always conserved. We love in science whenever something is always conserved because it makes that calculation so much easier to do. Think about in chemistry, we would not be able to do half the things if we didn't know mass was conserved, or the law of constant proportion, which just says all the atoms are conserved. In physics, we have energy is always conserved, but you guys did have known before, but now we're dealing with motion. The idea that a velocity and a mass, the amount of motion something has to be conserved. It can maybe go from one object to a different object, but that motion, that core motion, needs to be conserved. If you think about an explosion, by the way, this is a great example. Think about an explosion, right? The motion of those objects, right? If you added all those motion objects together, that motion needs to be accounted for, even though it's broken up into pieces. Of course, if you have an explosion, the same explosion might break something into small pieces that move quickly or large pieces that move slowly. So yeah, we did 3 examples. We did first a collision where the 2 objects stuck together. And to do that one, relied on us looking at, well, what was the net mass here. We sort of broke that down and we said it was moving slower. Then what we did was we did 2 examples. We did one example where we looked at passing the momentum, so one object hitting another one and making it speed off really quickly. And we found out, okay, well, what does the mass have to be in order for this to work? And then we did an example of, well, what happens if the second object is really, really big and it bounces back? And yeah, we sort of looked at this momentum here. We didn't talk about other types of collisions that we could have talked about. We didn't talk about like what would happen if you had a really massive object crashing into a really small object going the opposite direction. And this is the classic example of a car, crash, or it's not a classic example, but a car crashes into a truck. And then afterwards, well, the truck's going to win. So afterwards, that truck starts moving, the truck / car are moving at a slower speed, but they're moving in the other direction. Again, you can calculate that. You have to remember that the velocities are negative with respect to each other, so that's why the velocity of the truck will go down, not just because it's got an extra mass, but because it will lose some of its momentum, will be cancelled out by the fact that it's hit a car going in the opposite direction. So that's something that you could look at as well. We didn't do that one there. But we sort of talked about momentum here in a fair bit of detail. We're going to move on to talking about impulse. Now, what is impulse? Okay, well, the best way that I thought about talking about what impulse is to sort of start off by going back to that same question we just did. Of a 2 kilogram car bumping into the 6 kilogram car and bouncing backwards. But we're not actually going to care. I actually don't care about that 6 kilogram car at all. So what we're going to do is we're going to take this question. We now know that that first car is moving 4 meters per second, and then it's going backwards at 2 meters per second. We're going to completely ignore that, and we're just going to look at the car. Initially, it was going forwards at 4 meters per second, and then it's going backwards at 2 meters per second. And what I want to do is I would like to look at, well, what's going on here? If I had a look at this, I could say, well, initially my momentum of the car. Now it's going to be like the momentum is not conserved. And you might be like, oh my God, so the momentum's not conserved. In this case, yeah, sure, the momentum won't be conserved, but that's because some of it gets passed to another object. But we can still look at the momentum. We can still go the momentum equals the mass times the velocity. It's going to be 2 times 4, which is 8. And we can still look at the momentum of the car at the end, which is 2 times -2, which is -4. So there's a pretty big change in momentum. If I wanted to look at the change in momentum, and this is just like the question I just did, I'd go -4, take away 8. So there is 12 kilogram-meters per second change in momentum here. I want to look at the speed of the momentum change. So how long did it take for the initial momentum and the final momentum? How long did it take to change from the initial momentum to that final momentum? Well, I want to explore this equation with you guys. So the speed of the momentum change is going to be the final momentum minus the initial momentum, which is just going to be, mvf, so for final momentum, minus mvi. And we want to know how long does it take to change those momentums, so the delta t. But I wanted to sort of look at this formula for a bit and think to yourself, well, let's have a look here. We know that the final moment, the final speed and the initial speed, they're both being multiplied by the same mass, 2, 2. So we could actually rewrite this as just being mass times the final speed minus the initial speed over delta t. You know what? Instead of going final speed minus initial speed, let's just go mass times the change in speed, delta v over delta t. You know what? Let's just take mass out of the whole thing altogether. Mass times delta v over delta t. Actually, delta v over delta t is a change in velocity over time. A change in velocity over time, that's just going to be m times a, or ma. Now, mass times acceleration. Mass times acceleration. So this is the speed of the momentum change. Mass times acceleration, we already know what that equals. Mass times acceleration is actually equal to force. And that brings us to our new idea, and this is leading up to our idea of impulse. What we end up with is this. Force is actually equal to a change in momentum over time. Force is caused by a changing momentum over time, or delta P over delta T. It is exactly the same as F equals ma. In fact, from what I understand is when Sir Isaac Newton first came up with Newton's second law, he didn't say force is equal to a mass times acceleration. He said force is a change in momentum over time. And that gives us an idea of, this is an interesting way to look at Newton's second law. You guys may have been thinking to yourself, hey, momentum is completely separate from Newton's laws and kinematics, but we already know one, it has to be related to kinematics because we're going to have velocities essentially. And now you can see that it's related to Newton's laws because great, you've now got an idea of how a change in momentum is only possible because of a force. The only way that we can have a forward momentum of 8 and a backwards momentum of 4, the only way for that momentum to be changed, to go from here, the only way to go from here to here is with a force. But not only that, but we need to apply that force over a specific amount of time. Now this force-time relationship is how we get our idea of impulse. Let's talk about impulse. Impulse is a change in momentum over time. But if you think about it, impulse is a change in momentum. It's not momentum, it's a change in momentum. Sorry, let me rephrase that. We use the symbol I for impulse, and I equals F times delta T. So that's why it's equal to a change in momentum and not a change in momentum over time. Impulse is like how long you're applying a certain force for. You might need a certain impulse to change momentum of an object. You might want to change the momentum of a ball from 0 meters per second to 100 meters per second, and the ball might weigh like 100 grams. Now you can change the momentum by applying a strong force over a short amount of time, or you could apply a small force over a long time. So yeah, that's how you could think about it. I will point out, of course, that how do you measure this? Well, you would measure that is you could measure that by, sorry, forgive me, I'm just changing something here. Never mind, we'll figure it out. It's measured in Newton seconds because the measure of forces, Newton's the measure of time is in seconds, so Newton seconds. I should point out, it's not written on this slide, but I will add this here. It is a vector quantity because force is a vector, so it's a vector quantity. So when we talk about impulse, you should give a direction: forwards, backwards, upwards, left, right, so on and so forth. Impulse is equal to a change in momentum, so that's why I've got F delta T equals delta P, a change in momentum. So yeah, and if we think about it, force is usually always conserved. So if you want to get a change in velocity, you have to apply a force over a certain amount of time. If you want to change the speed of something by a lot, you should apply a large force over a long time. In fact, the longer a force is applied, the greater the change in momentum, the faster the object. An example here that I'm going to give you guys is something called follow through. This applies to golf. It applies to tennis. It applies to baseball. It applies to cricket. It even applies to a degree to soccer as well. What happens is that you follow through with your club to increase the time your ball and the club is in contact. What you want to do is, even once you've hit the ball, you don't stop the club once you've hit the ball. You keep moving through your swing. What that effectively means is that once you've hit that ball, you are going to keep pushing that ball with your club for as long as you can. You want to maximize the amount of time you're applying that force. If you can maximize the amount of time you're applying for that force, you will end up with a large impulse. And a large impulse will mean you end up with a high amount of velocity change. You will be able to increase that velocity by a lot. The same is true as if you're playing soccer. If you kick a soccer ball, if you just kick the ball with your foot, then that would would go somewhere. But what they suggest usually is that you sweep the ball along with your foot as quickly as you can. And what that does is it increases the amount of time that your foot is applying a force to the ball, which will make the ball go faster. These are ways that you can, harness the idea of impulse. And yeah, you could draw this example from many, many other places, but usually it's referred to as follow through. I even used to do this even with archery. We would do a sense of follow through. You would actually keep moving your hand backwards after you've released the string, because then that kind of keeps a bit more of a fluid movement. But it's a bit different because you're not actually applying the force after that point. But yeah, I guess the thing would be is you hold the bow up for a while, even after you've let go of the string. You don't let it go once you've let go of the string, because then it wouldn't work. We're not going to talk about too much there. It's a bad example. We're going to move on now to talking a little bit more about some other examples of impulse. So impulse equals force times time, and it equals change momentum. So we're going to look at this formula. I'm going to change this formula slightly. We're going to look at this formula instead as force equals a change momentum over a change in time. Now this is still the same formula. I've just moved the delta t. I've moved that delta t to the bottom. What you could think about in this case is a change in momentum. In a car accident, your head will go from 60 kilometers an hour to 0 kilometers an hour. That's a fixed change in momentum. Your delta p is fixed. If your head weighs, I don't know how much an average human head weighs, let's call it 4 kilos. If your head weighs 4 kilos, if your head weighs 4 kilos and you're going from 17 meters per second to 0, that's roughly about 17 meters per second is roughly what, that's roughly the 60 kilometers an hour. 4 times 17, you're losing 68 kilogram meters per second. Okay, you have to drop 68 kilogram meters per second. Now, how you lose that momentum is entirely up to your car. You could lose that momentum very, very quickly. How could you lose that momentum? By passing it to the windshield or the steering wheel of the car. If you smash your head into the steering wheel, then that will drop that 68 meters per second. That will change that momentum very quickly. And that's not a good move, because of course I don't want to lose that momentum really quickly. Why is it bad to lose that momentum really quickly? Well, if you lose that momentum really quickly, if you go 68 divided by, let's say it's 0.1, that's going to equal 680, 0.1 seconds. That's going to be 680 newtons. I do not want 680 newtons applied anywhere near my head. I do not want 680 newtons applied to the thing that does the thinking in my body. Now, what if I could change this number down the bottom? That would be really great. If I could maybe change it to be 680, let's say, even if it was just 4 seconds. 68 divided by 4, sorry, not 680. 68 divided by 4, even that is going to be a bit preferable to me. That's going to mean that I'm going to experience 17 newtons. Still going to hurt, but it's not going to be as painful. And so I want to experience that change in momentum over a longer time to get a lower force. And this is why we have airbags. Airbags allow our head to come to rest. So we still need to lose that 68 kilogram meters per second, but it allows us our head to lose that 68 kilogram meters per second over a longer time. And so therefore, because we're going into that cushion of air, and because of that, we experience a lower force. We would only experience 17 newtons worth of force. This is the same reason as well that cars have something called a crumple zone. I'm not sure if you've heard of a crumple zone before. What a crumple zone is, let me try and draw a picture here. It's going to be amazing. Look at this picture. What a crumple zone is essentially it's part of the car that's designed to buckle. What happens is that when you're in a car accident, part of your car is designed to get squashed. And the whole reason that it's designed to crumple is because it increases the amount of time of the collision. If you can increase the amount of time of the collision, then you will decrease the amount of force. You'll still have to go from 17 meters per second to 0, but you want to slow down as slowly as possible. You want that acceleration to be really, really low so that the force that you feel is really low. That's what we're trying to get across here. And that's another way you can explore impulse. It's just by increasing that time, changes that force. Let's go have a look at another example, of course, is the brakes. In a car accident, you want your wheels to stop fast. You don't want your wheels to go slowly. You want your wheels to be quickly stopped so that you can, not die. So especially if you're driving your car and you're about to crash into another car, you want to be able to put your brakes on quickly. So therefore, instead of again, let's say that your car, let's say you're going from 17 meters per second to 0. And let's say that your car weighs, 1,000 kilograms. Then that means that you need to lose 17,000 kilogram meters per second. And you want to do that this time in a very, very short time. Let's say you want to do that in, 0.1 of a second. That means you're going to need a force of 170,000 newtons. And that's why your brakes apply so much force. Your brakes apply such a large force to every single one of your wheels because it wants to drop that force. It wants to drop that speed really quickly. So that's why you end up applying a lot of force onto your brakes. Your force, by the way, your brakes work, and this is an example of the disc brake disc brake over on the left. How they work is that they push these pads against your wheels and actually slow them down. They actually cause a huge amount of friction. They get very, very, very hot. And because they lose their energy into the form of heat. But that's how they do it. They apply a large amount of force over a very, very short amount of time. So yeah, the amount of force that you need to apply in order to change the momentum quickly is very, very large. Whereas the amount of time, when you're in a car accident, you want the amount of time of the accident to be very, very long so that you don't experience very much force in the head. Now that's just 3 examples of impulse and how we can use impulse to understand situations. But ultimately, you can't use impulse without first understanding what its relationship to momentum is. I do want to point out, in your textbook, there is a bunch of other ways that I'm not going to go through about other explanations. They talk about your legs bending as kind of like crumple zones for your body. If you bend your legs, then you're less likely to tear things. This is moving your hand when you're trying to catch a fast moving ball, because then that means that trust me, I've tried to catch a cricket ball. It hurts like hell. So that's where you have to move your hand back as you catch it to kind of slow it down. So you're not going to hurt your hands much. And of course, if you don't want to catch a ball like that with your hand because it's going to hurt, use gloves, because they actually with pads in them, because they actually soften it. And then another one there is protective footwear as well. When you're running and stuff, try to use footwear with big, like if you look at running shoes, some of them have got lots of foam in them to sort of ease your foot when it hits the ground, so that you're not changing that speed so quickly, so that you're not causing as much force on your knees. Saying that though, they've started to put like springs in running shoes, and I'm not sure how. That's fine, but it's like, some people, like I said, it's like cheating because you're getting propulsion from the ground, but still good for use. For us, we don't have to do springs because springs are a year 12 concepts. Hooray! Screw springs. If you want to read these, by the way, these are in your textbook. I'm not going to go through them. I pretty much already did them. Let's do this quick question here. Very similar, in fact, almost the same as the question we did today in the attendance question. A 30-gram squash ball hits a wall horizontally at a speed of 15 meters per second and bounces back in the opposite direction, 12 meters per second. It is in contact with the wall for an interval of 1.5 times 10 to the negative 3 seconds. What is the change in momentum of the squash ball? What is the impulse on the squash ball? What is the magnitude of the force exerted by the wall on the squash ball? I want you guys to calculate for me. I want you guys to do the first one. I want you guys to do A. You guys should be able to do A without my help because we just went through it. So do A. This time, pay attention to the directions this time, ladies and gents. I'll be right back. I'm going to quickly heat up my coffee a little bit because it's a bit cold. And by the time I get back, I expect you guys to all have answers. And I want you guys to write those answers. Write those answers in the chat, but don't push enter. When I come back, I want you guys, everyone to push enter. And then everyone should be put all of their answers up at the exact same time. And yeah, then there can't be any shame because I won't have time to be able to go through and find out who got it wrong. So go. Okay. Are we ready? That was 20 seconds. I know that because my microwave said it was 20 seconds. So let's go and let's put our answers in the chat and then I want you to push enter. So we should all do it at the same time. Actually, let me quickly work out the answer too. Where's the change of momentum? Oops. Okay, yep, I'll go an answer too. We should all put our answers in the chat and I want everyone to push enter in 5, 4, 3, 2, 1, go. Enter. Oh my God, look at that. Look at that. It's the most amount of answers I've ever got. That's, oh my God, Kelvin, you did all of them. 0.81, negative 0.81, negative 0.81, negative 0.81. Really good. Yep. All right, cool. So that was actually what I got. So let's go through question A, B, and C. Rapid fire, ladies and gents. Question A. What is the change in momentum? A change in momentum is going to be equal to the mass times the change in velocity, which is going to be 0.03 because we're going to change that into kilograms times the change in momentum, which is going to be equal to v minus u, which is going to be 0.03 times the final velocity. We'll go with that being negative 12 minus the initial velocity, which is 15, which is going to be 0.03 times negative 27, which came out to be negative 0.81 kilogram meters per second. Or you could think about that, and the reason it's negative is you could say, well, positive is, well, it doesn't matter. It's just negative because it's going the opposite direction. What is the impulse? Well, the impulse equals a change in momentum. So therefore, the impulse is equal to negative 0.81 kilograms meters per second, or negative 0.81, sorry, or negative 0.81 Newton seconds. Now this might be a bit weird for you, but you can actually, because impulses are changing momentum, you don't actually have to do anything. It's actually the same thing. You can measure that in Newton seconds. You can measure that in kilogram meters per second. The two are interchangeable. As long as, yeah, the two are interchangeable. And you can actually go back to that previous example that I showed you and figure out why they're interchangeable. For C, what is the magnitude of the force? Thank God we don't have to calculate the direction exerted by the wall on the squash ball. So impulse equals force times change in time. Now our impulse is 0.81 and our change in time is 1.5 times 10 to the negative 3. So therefore 0.81 divided by 1.5 times 10 to the negative 3 equals our force. Now you guys might be saying, sir, why did you drop the negative sign? I don't need the negative sign. I just need the size. I just need the magnitude. So it doesn't bother me what direction that force is acting. 0.81 divided by 1.5 times 10 to the negative 3 gives us 540 newtons. And that's our force that we're going to experience here. That's the force that's going to push it and change that speed. Now, if that was in contact with the wall for a longer time, so like 1.5 times 10 to the negative 2 seconds, or even just 1.5 seconds, you wouldn't need to apply such a high force. So because it's only in contact for a fraction of a second, we need a high force. And I want you to think about it. When you bounce a ball off a wall, you don't really think about how long that ball is actually touching that wall for. It's probably not touching it for very long, especially if you use a hard ball. It's probably just going to touch it for a second. So it has to transfer a lot of force in a very short amount of time. Because it needs to change its momentum a huge amount in just like a fraction of a second. So there's A, B, and C for you. As I said, you might not be aware that you can write impulse as, I did say initially, it has to be in Newton seconds. That's a lie. You can do it in kilogram meters per second. I want to see how, sorry, Kelvin gave all three answers. Close. Yeah. Oh, okay. Cool. All right. Anyway, so I see what happened here. That's fun. So that's how you would do those types of questions. So all you've got to do is the change momentum is the same as an impulse. These two things are the same. Of course, the magnitude of a force, you do still need to use the FT formula, but that's fine. You should be able to hopefully figure that out with some practice. There is one more type of question I want to show you guys, and that's going to be the end of the lesson after that. I think I'm going to give you guys pretty much all of Thursday to work on some questions, because I've spent a lot of today talking at you guys, so you deserve some time in class to work on questions rather than me just setting it all as homework. I don't think that's very fair. What we're going to do is we're going to look at this, and this is going to be very similar to a this is going to be very similar to a what am I looking at? A force, a displacement time graph, and we're going to look at an impulse from a graph. A student records the force acting on a rubber ball as it bounces off a hard concrete floor over a period of time. the graph shows the forces acting on the ball as it collides with the concrete floor. So what we have is a force time graph. Note, pay attention, ladies and gentlemen. Force is given in milliseconds here. But interesting, of course, the area is going to be equal to force multiplied by time. So the area is going to equal the impulse. So let's calculate the impulse that this ball experiences, or the average impulse, you might say. Now, the impulse is going to be the area under the graph. You could do this a couple of ways. Ladies and gents in chat, I want to know: do we feel like being lazy, or do we want the easy one or the lazy one? What do you guys want? Lazy or easy? I can do either or. I'm just going to take whatever this first answer is. I'll take lazy or easy. Either or. Both. No, not both. That's not one of the options. None. That's also not one of the options. Lazy one. Thank God. Okay, we'll do the lazy one. The lazy one is this. We have to find the area on this graph. What kind of shape is this? This is a trapezium. To find the area under a trapezium, you have the formula area equals half A plus B all divided by 2 times the height. Now, in this case, the impulse is going to be the area. So we've got A, B, and the height is this one here. The easy way is to break this down into 2 triangles and a rectangle and then deal with that, but we're just going to deal with it all at once. A in this case is the top is going from 2 to about 8. So that's 8 minus 2 is going to be 6 plus B, which is the base, which is 13. 6 plus 13. I'm just going to multiply this by 10 to the negative 3 because I'm going to convert it to seconds. Okay. And then what we're going to do is we're going to divide by 2. We're going to multiply by the height, which in this case is 60 newtons. Putting all that into the formula once, 6 plus 13 equals 19 times 10 to the negative 3 equals 0. Hold on. 0.019 divided by 2 times 60 is going to be 0.57 Newton seconds. Okay, upward, because we're bouncing the ball upwards. Now, and of course, we could do this instead as 3 triangles. We could go half the base times the height of the first one, plus the second one, plus the third one. But I've just been lazy and I've just done it all as a trapezium. But yeah, you could do it like that if you wanted to. I'm not doing both, but yeah. I want to point out as well, before we move on to the last little question down the bottom here, I want to talk about what's going on in this graph. So if you look here, the force builds up. Okay, and I wanted to talk about, well, why is the force building up for? And the reason for that is, if you imagine a ball and it hits the ground, initially when it hits the ground, the first thing that's going to happen to it, that ball, is it's going to touch. It's going to experience a little bit of force. But then what's going to happen is that ball is going to get deformed. And you're actually going to have a sort of a ball that looks a little bit like this. To the point where you've almost got a ball that's going to look a little bit like that, sort of. I don't know, if you will. And then that ball is going to start bouncing back up. So you're going to have, it's going to move up to looking more like this. Until eventually you have the ball just touching. And that's actually what's happening here. So this part here equates to that part here, and this part here where it's applying a force and the force is slowly getting less and less and less, and that's because it's moving further and further away from this, less and less of it's touching the surface. So that's why you end up with a weird trapezium shape. So let's say if that ball had a mass of 0.5 grams and was initially traveling downwards at 5 meters per second after the bounce, what will the ball's new speed be? Well, let's calculate the initial momentum. The initial momentum is going to be 0.05 times 5 is going to become 0.025 kilogram meters per second. I think I got that wrong. I think I accidentally 0.0, I think I did get that wrong. 0.05 times 5 is actually 0.25. So it's going down, but this one's going downward. So we're going to have to put a negative here because it's going in negative speed, negative initial velocity. So it's going to have its momentum increased by 0.57. So P final is going to be P initial plus the change in momentum is going to be negative 0.25 plus 0.57 equals negative 0.32, and of course 0.32, no, positive 0.32 equals mass times velocity. The velocity is going to be 0.32 divided by 0.05 is 6.4 meters per second. I've made a mistake here, ladies and gents. Hopefully you guys have been like, whoa, 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 that doesn't make sense. Yeah, it doesn't make sense that it bounces off the floor with a higher speed than the is going towards the floor. So I've made a mistake here. Realistically, I should have changed this question. It should have been falling towards the floor at a faster speed. We're going to ignore that and just pretend it's like, oh, you know, it makes sense. But yeah, in general, this is how you would do a question like this. Are there any questions on this aside from my glaring mistake? I also apologize, guys. I know that it's hard to see this because it's against the blue background and it's.
So isn't it 0.32 instead of negative?
Yes, you're right. Yeah, so good. I'm glad that you guys are understanding this. The last little bit here, and this is going to be the last thing I teach you guys today, is going to be this guy here. And this is a not so straight graph. Let me just fix this, shall we? So a not so straight graph. How do we do a not so straight graph? Well, a not so straight graph is we're just gonna do. I just want to show you guys how to do this because, and this is actually the one that they go through in the exercise. And it sort of says estimate the maximum force acting on the athlete's foot. Sorry. The following graph shows a net vertical force generated on athlete foot strikes an asphalt on a running track. So it's the same idea. Initially, the foot comes down. The other one stops the momentum. That's probably, sorry. Vince just pointed, sorry, a student just pointed out that they can't access it because it stops the momentum. My guess is because the PowerPoint hasn't been updated yet, because probably I only fixed this up last night. It automatically updates every couple of lessons. So what it should do is it should update, but if it doesn't update, I will put a new link to this up on the Google Classroom. But we'll get to that in a little bit. The following graph is, I'm just going to finish this question off first, though, Vince. Estimate the maximum force acting on the athlete's. Sorry. So yeah, it's the same idea here. Again, initially, only a little bit of force can be pushed on the foot because the foot's barely touching it. Then the foot completely gets pressed against the ground, and in the end, as the foot's coming off the ground, less and less force can push it of the ground can push on it. So therefore, what is estimate the maximum force acting on the athlete's foot during the contact time? During the contact time, the maximum force is going to be about there. I'd say that's 1,200 newtons. Then it says estimate the total impulse during the contact time. Now to do this one, and this is a similar question to what we did before, is that we have to try and find out what the area under this graph is. Now, if we had if we knew the equation of this graph, we could use some fancy dancy maths to figure it out. Because we don't, we're going to just draw what we think the graph. We're just going to draw a rough estimate. There are two ways we could do this. Number one, and this is the way, I'm not going to use this way. The first way you could do this question is you could count the boxes. Same. And that's the same method that we used for calculating the displacement and under a velocity time graph. We could count these boxes. I'm not going to use that for this method just because but instead I'm going to do this. I'm going to assume that we've got I'm going to draw a line here. I'm going to draw a line down here. Actually, hold on. I've got a ruler next to me. I'm going to draw a line here. I'm going to draw a line from here down to here. And I'm going to draw a line from here down to here. And we're going to do another trapezium. And we're going to pretend that this trapezium represents this graph. And it sort of is close. It's going to be under representation because, but it's going to be close. So the second method is, of course, to use a shape. Use a close shape. You could instead maybe use a triangle. You could instead draw a triangle to fix this. But I think this trapezium should do nicely. The area of a trapezium, god damn it, why does that keep going away? The area of this trapezium is A plus B all divided by 2 times the height. You don't need to put the brackets there, but I like to do the brackets because that's usually what's there. As long as you remember to do that first. Now the A plus B, the A to B is roughly going to be, A is going to be, we're going to call that from 20 to 50, so we're going to call that 30. Plus B, which is going to be from 0 to 70. And we're going to multiply that by 10 to the power of -3 because it's in milliseconds, and I want my answer to be in seconds. divide by 2. I'm going to multiply by the height. And the height of this is actually not the top. I've actually done it at about 1,100. So it's going to be 100 times 10 to the power of -3, all divided by 2 times 1,100, which equals, okay, 100 even -3, which is a bit silly for me to actually do. It's just going to be 0.1. It's like saying 100 divided by 1,000, which is going to be 0.1. Divide that number by 2 gives me 0.05, but then multiply that answer by 1,100 gives you, or it gives me 55 newtons second upward, because it's being pushed upward because it's a foot. Now, if you get a slightly different answer, that's perfectly fine, because the thing here says to estimate. In a proper exam or test, there would be a range of acceptable values. So you would have to hit somewhere in that range. Are there any questions on this not so straight graph? Well, there is a question. It's very unusual. So, why did you have to multiply by 0.01? Good question. The reason I did that is because this is in milliseconds. Now, if this was in seconds, I wouldn't have done that. If this was in micronewtons, I would have changed the height as well. But because I want the answer to be in seconds, that's why I changed it. You could also think about changing it in grams. I could instead, and if you really don't like that, then you can actually just make sure that you instead you could, yeah, where did the times 10 to the -3 come from? It's the same thing. 1 second equals 0.001. 1 millisecond equals 0.01 second, or 1 times 10 to the power of -3 seconds. The other way you could do it is instead go, it's 0.03 plus 0.07 divided by 2 times 100. That will get you the same answer. And the reason we use 0.003 is because it's 30. That's how many milliseconds it is. It's 30 milliseconds. It's a different way to do it. A different way to do the same one. Same question. Anything else? Any other questions? I will finish up then.